Now we will discuss propagation delay in logic gates and the questions based on propagation delay. So what happens actually in a logic gate? So to understand this, we take an example of a simple NOT gate. The output expression of a NOT gate is y is equal to complement of A. So what it actually means, if we have an input waveform A given in this way, so output is always the complement of the input. It means if input is 0, at that time output should be 1. If input is logic 1, output should be logic low. So what we are expecting is a waveform like this. Means when input is 0, output should be 1. This is the waveform of y that we are expecting. And if input is 1, output should be 0. We get a similar waveform but with a minor or a small change. Whenever there is a transition in input, transition at output will definitely occur, but after some time, not instantaneously. What is a transition? Transition is simply change from logic low to logic high or from logic high to logic low. For example, this is a transition and this is also a transition. So obviously, if there is a transition in the input, there will definitely be a transition in the output, obviously. But the transition will not occur at the same instant, it will occur after some time. Means the actual waveform of y will be, see, input is 0, output will be 1. Input transition at this instant, output transition will not be exactly at the same instant. Output transition will occur after some time. So no doubt there is a transition in the output from logic high to logic low. There is a transition in the output from logic high to logic low. But the time of transition is not exactly at the same instant where it happened in the input. There is a delay in the transition at the output with respect to the transition in the input. And this delay or this difference is called as propagation delay. This delay in the output transition with respect to the input transition is called as propagation delay. This delay in transition at the output with respect to the transition in the input is called as propagation delay. Is called as propagation delay. Now, why this propagation delay happens is very simple, obvious reason, because in this logic symbol there is a circuit inside. If there is a circuit inside, the input signal has to pass through the circuit to get or to obtain the output. The delay in obtaining the output is basically the propagation delay. For example, let me show you the actual circuit of this NOT gate. See, this NOT gate can be designed using various technology. One of the technology is RTL, resistor transistor logic. In resistor transistor logic, how to design this NOT gate is quite simple. This is a simple circuit of a RTL NOT gate. This is your supply VCC. This is your collector resistance. This is the place where you check your output. This is where you apply the input. So you apply the input at the base terminal. You check your output at the collector terminal, and this emitter is grounded. So when you give your input signal at this terminal, you will not get the output signal at the same instant. Or I can say in this way, if you make a change in the input at this terminal, the change will obviously not occur at the output on the same instant. There will be a delay in the transition at the output. If, for example, I want to draw using CMOS. So, CMOS consists of PMOS and NMOS, like this. This is the circuit of a NOT gate in CMOS logic. This output is Y, this is supply VDD, and this is your ground. This is your PMOS and this is your NMOS. So in the same way, if you make a transition at the input, obviously transition at the output will not occur at the same instant. It will occur after some delay. And this delay is called as propagation delay. So, propagation delay is the delay which we get in output transition with respect to the input transition. So, what we are saying is very simple. If you make a change or transition in the input, there will definitely be a transition or a change at the output. But that transition or change will not occur instantaneously. It will take some amount of time. And this amount of time or this delay is called as propagation delay. Now, for solving the questions based on propagation delay, we will be using very simple concept. Such simple that you will never get confused however complex the question may be. That simple concept is, see, there is a propagation delay in this NOT gate, but what you do, first you draw the output considering delay is equal to 0. First, you do not consider any delay in the circuit, you just draw the output without considering the delay. Then what you have to do, you have to simply shift the waveform right hand side by delta t. Because there was a delay in the logic gate, you have to shift the waveform right hand side by the propagation delay amount delta t. Let us try to implement in the next question. See, question number 17. Again, all these types of questions are very simple. Just follow the approach we are discussing in this video. It is given all gates have propagation delay of 20 nanosecond. Some particular input condition is given, A is equal to C is equal to 0 and B is equal to 1 until time t is equal to 0. So this is your time t is equal to 0, I have shown with the dotted line. This is t is equal to 0. So until t is equal to 0, A and C are equal to 0 and B is equal to 1. At t is equal to 0, all inputs flip. Flip means complement. A and C becomes 1 and B becomes 0. You can see here. A and C becomes 1 and B becomes 0. Now question is, for the time t greater than 0, output Z is equal to 1 for how much duration? This is your output Z. You have to check this output Z is equal to 1 for how much duration. So we will try to solve the question step by step. So starting from the left hand side, the first waveform is B complement. First I will get B complement, then only I can reach this AND gate. So this waveform is B complement. This waveform is B complement. Okay. Now, as I told you, draw the waveform of B complement considering there is no delay. Draw the waveform of B complement considering there is no delay. So write down. This is B, so B complement will be 0. If input is 1, output is 0, and if input becomes 0, output is 1. This is your B complement. But this B complement is considering there is no delay. But it is given all the gates are having 20 nanoseconds of delay. So what simply you have to do? You simply have to draw B complement. You simply have to draw B complement by shifting 20 nanosecond. Just shift this waveform 20 nanosecond. Shift this waveform 20 nanosecond. So this duration is 20 nanosecond. 20 nanosecond. So there was a transition in B complement from 0 to 1. We have a same transition from 0 to 1, but that transition will occur 20 nanosecond. At 20 nanosecond. Now come to the circuit B complement. We have got B complement. Next step is A dot B complement. Next step is A dot B complement. So see, this one is A and this is B complement. A and B complement. First consider there is no delay. A dot B complement considering 0 delay. Consider there is no delay in the AND gate. So AND gate output will be A dot B complement. This will become 0. See, from 20 nanosecond, B complement is also 1, A is also equal to 1. So this is A dot B complement. This is A dot B complement. This duration is 20 nanosecond. This duration is 20 nanosecond. But, okay, just I want to, it is exactly correct waveform, just I want to draw it with the red marker. So I am just changing it. Waveform is exactly correct, just the fact I want to use red marker. Because all the waveforms considering 0 delay I am drawing with red marker. Considering 0 delay I have drawn with the red marker. But there was a delay in AND gate also. How much was the delay? Again 20 nanosecond. So A dot B complement with a delay of 20 nanosecond. So what I have to do? I have to shift the waveform 20 nanosecond. I have to shift this waveform 20 nanosecond. So already it was 20 nanosecond. I have to shift by 20 nanosecond. This becomes 40 nanosecond. This becomes 40 nanosecond. Already there was 20 nanosecond. This becomes 40 nanosecond. Okay, now see. Now, next way is this one. Now I need A B complement XOR with C. A B complement XOR with C. So I will draw A B complement XOR with C, again considering 0 delay first. Again considering 0 delay first. See, A dot B complement and C. A dot B complement and C. See, this is 0. 0 XOR with 0 will be 0. See, C is 1. This is equal to 0. 1 XOR with 0 is 1. C is equal to 1. This waveform is also 1. 1 XOR with 1 is 0. This is the waveform considering 0 nanosecond delay. This is the waveform considering 0 nanosecond delay, and this duration is obviously 40 nanosecond. But this XOR gate also has a delay of 20 nanosecond. This XOR gate has a delay of 20 nanosecond again. This XOR gate has a delay of 20 nanoseconds again. So what we have to do? Simply shift the waveform 20 nanosecond on the right hand side. Shift this waveform 20 nanosecond on the right hand side. Shift this waveform 20 nanosecond on the right hand side. Shift this waveform 20 nanosecond on the right hand side. So this instant will be 20 nanosecond. This duration will be 40 nanosecond. So this instant will become 60 nanosecond. So this instant of transition is 20 nanosecond and 60 nanosecond. In between the transition, duration is 40 nanosecond. The question was output Z, this is your output Z, is equal to 1 for how much duration? Output Z is equal to 1 is for 40 nanosecond. Output Z is at logic 1 for a duration of 40 nanosecond. That is the only question for you. So answer is 40 nanosecond. So this answer is 40 nanosecond. This is the correct answer. Next, question number 18. In this question, a circuit is given. Again, waveform of input is given. This time it is asking how many transitions will be there at the output B. Important information given is there is no delay in XOR gate and any of the connecting wires. But there is a delay in non-inverting buffer. Buffer is obviously by default non-inverting, but still it is given non-inverting buffer. It means it is a buffer only. So this buffer is having a delay of 2 nanosecond. This buffer will be having a delay of 4 nanosecond. There is no other delay to be considered in this circuit. Only the delays to be considered are of buffer gate. See, buffer gate we already know it is like this. Buffer means not gate without a bubble. Buffer means not gate without a bubble. So whatever input we give, the same output we will get. Let's say we have an input waveform of this shape. This input waveform is applied to this buffer gate. So this output Y is also equal to A. So output Y is also equal to A. We are expecting Y to follow the exactly same waveform. But there is a delay in this buffer gate as well. So due to the delay, same transition will occur but not at the same instant, after some delay. And this delay is only called as your propagation delay. So there can be a delay in buffer gate as well. Buffer gate means whatever input you give, same output we will get, no doubt. But if you will make a transition at the input, the transition will be output will be obtained after some delay, and that delay is called as propagation delay delta T. Now let us start solving the question. So for that, what I will be discussing, or what I will be taking the notations I am discussing with you now. So I will consider this as A dash. See, A dash is not the complement of A, it is just a new waveform A dash. So this input is A. So now let me consider the output of XOR gate is C. So again this will be waveform C and this will be C dash. So what is the difference between A and A dash? A dash is the delayed version of A by 2 nanosecond. In the same way, C dash is the delayed version of C by 4 nanosecond. And finally, we will get the waveform of B. So now let us start drawing A complement first. See, we already have been given A. We will continue with A complement and then so on. Okay. So this waveform A is given to you. Now what about the waveform A dash? A dash is the delayed version of A by 2 nanosecond. So delay of 2 nanosecond. Delay of 2 nanosecond. This is A dash having a delay of 2 nanosecond. Now what is C? C is equal to A XOR with A dash. A XOR with A dash. XOR of both these. So 0 XOR with 0 will be 0. 1 XOR with 0 will be 1. 1 XOR with 1 will become 0. So this is the output of XOR gate, and we will not delay this output as XOR gate is given as 0. Means there is no delay in XOR, so no need to shift the output of XOR gate. No need to shift the output of XOR gate. So now we need C dash. So what is the difference between C and C dash? C dash is the delayed version of C by 4 nanosecond. See, this instant is 2 nanosecond, this instant is 0 nanosecond. Now C dash is the delayed version of C by 4 nanosecond. Shift this waveform by 4 nanosecond. If we shift this waveform by 4 nanosecond, see, just this waveform I have shifted by 4 nanosecond. So 0 plus 4, this will become 4 nanosecond. 2 nanosecond plus 4 nanosecond, this will give you 6 nanosecond. This is the waveform of C dash. Now, what is the waveform B? B is equal to C XOR with C dash. C XOR with C dash, I need XOR gate. C XOR with C dash. So XOR gate means 0 and 0, 0 and 0, XOR gate will be, just a second, 0 and 0, XOR output will be 0. 1 XOR with 0 will be 1. 0 XOR with 0 will be 0. Again 0 XOR with 1 will be 1. Just XOR of C and C dash. XOR of C and C dash. So this is the waveform of B. How many transitions it is having? Let us see. This is the first transition, second transition, third transition and fourth transition. There are 4 transitions in the waveform of B. That was the question. So answer is 4. Okay. So we have considered delay only for buffer. A dash is the delayed version of A by 2 nanosecond due to buffer gate. C dash is the delayed version of C due to buffer gate. Otherwise, we have not considered any delay in this circuit. So output of XOR gate, we are not shifting right hand side. Output of XOR gate, we are not shifting right hand side. One more question on propagation delay, question number 19. In this question, there is a delay in this NOR gate of 10 nanosecond. There is a delay in this XOR gate of 20 nanosecond. Input waveform Vi has a transition at T0. Vi has a transition at T0. We need to draw the output waveform V0. So let us solve in the same manner we have solved the last 2 questions. There is a transition in Vi. There is a transition in Vi at T0. There is a transition in Vi at T0. So now we will draw, see this NOR gate, both inputs are connected. So this output is Vi complement. Basically this NOR gate is acting like a NOT gate. So waveform of Vi complement. Vi complement will be complement of Vi. Complement of Vi. Complement of Vi, but obviously considering 0 nanosecond delay or without considering any delay. Complemented waveform of Vi without any delay, but this NOR gate is having a delay of 10 nanosecond. So Vi complement we will draw again with a delay of 10 nanosecond. Shift the waveform 10 nanosecond right hand side. Shift the waveform 10 nanosecond right hand side. So this is T0, this is T0 plus 10. According to the question, this is T1. According to the question, this is T1. According to the question, this is T1. Okay, now see. This is Vi complement and this is Vi. XOR of Vi complement, XOR of Vi complement and Vi. One thing you must be noticing, if I have to use Vi complement further, I will never use this waveform whose delay is not considered. If I have to consider Vi complement for further analysis, we definitely have to consider that waveform of Vi complement in which we have considered the delay, the given delay. So these two XOR will give me V0. Again V0, first waveform without considering a delay. So these two waveforms we have to make XOR operation. 0 with 1 will be 1. Both are 1, so it will become 0. This is 1 and this is 0. Again XOR will become 1. Again XOR will become 1. This is T0 and this is T1. But this waveform for V0 is without considering any delay. So waveform for V0 considering 20 nanosecond delay. Waveform for V0 considering 20 nanosecond delay, simply shift the waveform right hand side. Simply shift the waveform right hand side. So shifting the waveform right hand side by 20 nanosecond. Shifting the waveform right hand side by 20 nanosecond. T0 plus 20 will be T2 and T1 plus 20 will be T3. This is the correct waveform. You can check in your option. So the correct waveform is always at logic high except the interval T2 and T3. Except the interval T2 and T3. This is the solution of question number 19.